All right, so now we're going to start talking about chiral stereoisomers. And this is one of the trickier things that we're going to be doing this chapter. So I've broken it into 3 parts here. We're sort of going to be building towards this skill. First thing we're going to do is learn how to spot stereocenters and draw enantiomers. What the heck does that mean, right? So let's go in here. So first of all, what is a chiral molecule? So again, these are stereoisomers. Their connectivity is going to be the same, but their spatial arrangement of atoms is going to be different. For a chiral molecule, chiral is defined as an object that is not identical to its mirror image. Okay, that is the definition of chiral, meaning that if you take your molecule and you take its mirror image, you can't superimpose those two onto one another. A good example of another chiral object would be your hands or your feet. They're mirror images of one another, but you can't ever superimpose them on top of one another. Okay, so also chirality is called handedness as well sometimes. But yes, so this is a property that we're going to see in molecules as well. And if you have a chiral molecule, that means that there will be different stereoisomers. So again, first thing is going to be to spot stereocenters and draw enantiomers. So, and I'll define enantiomers here in a second, but let's just make sure that we can draw mirror images of a given molecule as well. Okay, so here I'm given this molecule and I want to draw its mirror image, right? So now the hydrogen is going to be sitting close to that mirror. I have my linear bond here, and then that goes up to the OH group. My ethyl group is still pointing into the board, and my methyl group standing out, right? So these 2 molecules are mirror images of one another. And what you should do is take your model kit and build something like this. You can just use different color beads, kind of like they've done in this one here. Build one molecule and then build its mirror image. And if all 4 of your colored beads are different colors, you'll see that it's impossible to turn them in such a way that everything overlaps, that they superimpose onto one another. Something that's really, really, really difficult to see just in 2D. I swear the model kits make a big difference here. And again, this has a lot, goes back to pharmacological use. So chirality is really important in the sense that 2 chiral molecules, they have a lot of the same physical properties, right? They have the same melting point, boiling point, all that good stuff. A lot of the same physical properties, but again, pharmacologically, they could be different. And I sort of just go back to this image here. This is an example of 2 chiral molecules here. And you can see that they have this different spatial arrangement. That means that one can't plug into that same keyhole that the other one fits into. So how do you know if a molecule is chiral? Okay, so this is the first skill we're going to learn, is you have to be able to spot a stereocenter. Molecules that have stereocenters are going to have chiral stereoisomers. What the heck is a stereocenter? A stereocenter is just a carbon that's in a tetrahedral, so that means that it's sp3 hybridized, and it's bound to 4 different groups. That's the key of a stereocenter, is all 4 of those carbon bonds are different. Okay, so here we have an example. Here's a CH3 over here, a chlorine. Now we have CH2, CH3, and then of course what's missing is that implicit hydrogen. So you see that all 4 of those bonds are different, right? That's what makes this highlighted in green here a stereocenter. Same with these other 2 as well. They both have different, all 4 of their bonds are different. Notice, here's a CH2 and here's a CH2, but I'm talking about how it extends, all the way out into infinity. Unless it's perfectly symmetrical, then you actually consider both, this whole side. So this is CH3. I guess what I'm saying is we could replace this with CH3, CH2, and we could replace this with CH2, CH2, CH3. And so these are two distinct groups. They're different from one another. Okay. And then let's just like look at some examples real quick of something that wouldn't be chiral, taking, or wouldn't be a stereocenter, building off of these examples. So what if I had something like this? This carbon here would not be a stereocenter because on either side are ethyl groups, right? So here's an ethyl, here's an ethyl. Those are not distinct from one another, so those would not be, so that would not be a chiral center. Likewise, and one of the trickier ones to kind of see is in this structure here, if I got rid of this double bond, then this carbon is bound to the same thing on this side as it is on this side. So this would also not be a chiral center if I got rid of that double bond, okay? So you're looking for 4 distinct groups. Okay. The last concept that we're going to introduce here is an enantiomer. Okay, an enantiomer, a pair of enantiomers, they always come in pairs. A pair of enantiomers are 2 molecules that are mirror images of one another. And that mirror image is not identical, right? So they're stereoisomers that are mirror images from one another, okay? So that would be what a pair of enantiomers is. This is kind of our, we got a few vocab words this chapter, right? Chiral being one, hopefully you can define that. Enantiomer is another one, right? So by vocab words, I mean weird sounding chemistry words that we got another definition of. Okay, and what I'm gonna do is I'm gonna draw this enantiomer here, right? And again, an enantiomer is a mirror image. So just gonna draw the mirror image of this. My chlorine atom there, right? So this would be a pair of enantiomers here. Now, one other trick I want to show you, an easy way to draw enantiomers, is look what would happen if I took this molecule here and I sort of like rotated it around this here, right? So I'm taking it and I'm flipping it over. Well, if I flip it over, then the bond, the chlorine that was pointed at me is now going to be pointed into the page. So this would be another way of drawing this pair of enantiomers here. And notice, kind of an easy way to do it is you just change your wedges to dashes. And if you had dashes, you would change them to wedges. That would be sort of a cheat way to draw enantiomers or mirror images. And again, you can verify using your model kit that by doing so, you've created 2 distinct molecules, meaning that they're not going to be able to superimpose onto one another. So this is, again, a pair of enantiomers. They are chiral stereoisomers. Okay, so what we're going to be kind of like building towards here is this nomenclature system where we're going to be able to classify these as being an R stereoisomer and an S stereoisomer. And those will be built into the name of the compound, just like we had with our cis-trans. But this is our first step, was just being able to identify stereocenters. So make sure you guys get that, and then we'll build on top of this, ending with that classification system.